Good morning, friends. Today we'll cover chapter 12 on Spark RDD, Repartition and Coalesce. So this is related to the number of partitions which are created when we create an RDD and how we can control, how we can increase the number of partition or decrease the number of partitions. So these are the two methods which are available to us, repartition and coalesce. But before we dive deep into these actual methods, let's revise. I think we have discussed this before as well, that how the RDT is created and how it is, how we have the number of partitions, worker threads, and all. But let's revise this before we actually write some unit test cases on repartition and coalesce. So when we have written our test cases and when we create our Spark conf object, we have always used the set master as local star. So as we have discussed, that list local stars means that it will create the number of worker threads equal to the number of cores of CPU I have in my laptop currently. So I'm running it in laptop. So again, in this submit applications, the Spark official conference page, the master URL, if you are marking it as local star, it means that run Spark locally with as many worker threads as logical cores on your machine. So this is what we have always been creating by using local star. So it means that it would, by setting this, the number of worker threads would be 4 because I have got 4 CPU cores in my laptop. And when I use this Spark context, Spark conf with having local star 4 number of worker threads, and call parallelize method on the data, and then it will create me a Java RDD. So as we discussed that I have like there are like two ways of this overloaded method for parallelize. One is just the data, and then without specifying the number of slices, it means that it will take the default number of partitions of 64 MB size. If the data is a multiple of 64 MB of size, it will divide that partition accordingly. So it would look like this, that once we call this parallelize method, or once we call the text file when we are reading from a big file, it will divide that data into 64 MB of chunk of size of data, and then it will distribute it across all the worker nodes that we have. For example, I have got 4 worker nodes or 4 worker threads. Then it will be distributing this RDD 64 MB each in each of these worker nodes. I'm saying it's 64 MB because it's based on the HDFS Hadoop file system block size, which is defaulted to 64 MB. And this is the advice, is the partition size in bytes as given in the, you can check the Spark RDD configuration page. So for HDFS, which is Hadoop file system that we are using in Spark underlying, and it actually has the default block size of 64 MB. So going back again, we have got a Spark config where we can specify the number of worker nodes or worker threads based on this local star or whatever, the set master. And we can just create the RDD by using the Spark context for the data that we have. And data, as mentioned, that it would be based on the 64 MB chunk size. So if we look at this diagram here, suppose we have got a list of data and we call this parallelize data method, then accordingly it will create the RDD with each of the partitions. Like it would be by default getting 4 partitions for 4 number of CPU of course, and it will divide the data accordingly. And then we can have narrow transformations where we can have like map, filter, and union, where each partition data would be worked upon for each of the like operations that we are performing. Like for example, map, it will map this data from one partition. In the same partition, it will map it to some other value or filter it to some other value. So this is for the narrow transformation. And for the wider transformation, which involves like group by key, reduce by key, in that case, the data would be shuffled because the data can be spread across various partitions. And when we are performing like the whole wide level of operation on based on a key or reducing it or grouping it, in that case, the whole data would be shuffled across all the partitions. It will not be just like a map or a filter, which will just move from one in the same partition. It will be across all the partitions, which will be a very expensive operation, and that will require a lot of shuffling, and the performance is impacted here. So this is the whole process of how RDD is created and all. Now let's go back to our topic of this chapter, repartition and coalesce. So this is where we can control the number of partitions by using these two methods. So let's go with the repartition first. So the repartition method, when we can control the number of partitions by specifying an integer number here. What it will do is that it will reshuffle the data in the RDD randomly, and it will create the equal size partitions across all the RDD across all the worker nodes. So what it will do is that if our RDD is like spread across several worker nodes, and we call repartition, and we repartition it, we can increase the number of partitions, for example, from 4 to 6 or 8, or we can reduce it as well from 4 to 2. Then it will reshuffle all the data. It will always call shuffling of all the data across all the nodes, across all the partitions to be precise. So here, if we go back to this official definition here, it's shuffle the data in the RDD randomly to create either more or fewer partitions. It depends on the number of partitions that we have given, and balance it across them. This always shuffles all data over the network. So this is an important point, and this makes this repartition very expensive operation. When we are dealing with billions of data and with billion of like not billions of data, but a lot of nodes or partitions, then it would be a very expensive operation, right? Because it will shuffling all the data over the network. The example is given here that we have got repartition 2, where we are reducing the number of partitions. Say for example, it's 4. Then when we call this repartition to back to 2, then it will create a new RDD, and this RDD would be created by just shuffling all the data from the previous 4 partitions to, and then comparing it to the 2 number of partitions to 2. But the shuffling would be taken care, would be done across all the 4 partitions. And the second method is for Coalesce. Coalesce is like an optimized version when we want to reduce the number of partitions. So it's an optimized version. So how it optimizes is that it's given in this word. It can decrease the number of partitions in the RDD to number of partitions, right? It cannot be used to increase the number of partitions. And it's useful for running operations more efficiently after filtering down a large data set. So this, as mentioned, that it is more efficient. So what it does is that it will not shuffle all the data over the network. If we are decreasing, say, for example, from 4 to 2, what it will try to do is that it will try to just shuffle the minimum number of partitions would be involved for shuffling the data. So, for example, if we have got, say, 6 and we want to reduce it to, say, 3, so it will just choose the only like 1 or 2 partitions to be merged over the existing partitions. By this, it will not cover all the partitions to be shuffled. So this is how it would. It actually is like internally, it's like more efficient than repartition, because repartition will shuffle whatever whether you're increasing or decreasing. It will shuffle all the data across all the partitions. But for Coalesce, it will try to like optimize it by just shuffling the minimum partitions that are involved to the existing partitions. Internally, it's like quite complex at how it is done, but at a very high level, this is how it actually achieves the better performance by decreasing the number of operations or shuffling. One last point before we actually jump into the test cases. So, what is the use of this Coalesce and repartition? So this can be the usage for this Coalesce is that suppose we are working on billion of data, like it's a very huge file or big data size file. I mean, this is where the Spark comes into picture, dealing with the big data, and we have performed many transformation and actions or reductions. I mean, after filtering that huge set of data, we have come to a point that the data that after all this filtering and mapping or reducing, it actually like filters down to a narrow set of data. Say, for example, from 1 billion, it reaches to say like 1 million of data left. And by default, I mean, as mentioned that we had got like 64 MB of partitions in the HDFS block. So, for example, after doing all this reduction and mapping and filtering, the data is reduced. So we don't need those number of partitions. We don't need like say 2,000 of partitions which was created before, holding that 1 billion of data. And after this reducing, we don't need that amount of partitions. In that case, Coalesce would be very useful. Never use repartition. Repartition is a very rare case, and because it's, as mentioned, that it's highly its performance-wise, it's not very good. So in the scenario that we just discussed, when we are reducing the data, then we can reduce the number of partitions as well by using this Coalesce method. In that case, it can actually affect the performance, because just maintaining that minimized set of data after all these reductions, then decreasing the number of partitions, that will help for further operations, because now we have reduced the partition. It doesn't need to the threads doesn't need to spread across all the partitions to do a particular operation. It can just do the same thing with the reduced number of partitions. So enough of the theory now. Let's jump into the IntelliJ in our next video, and then we'll see that how we can. In this we'll see that how the repartition and coalesce works, and we'll also do a benchmark that how the performance can be impacted by using both of these methods. So see you all in the next video.